Okay, so now why do we need to know what these structures look like, how the bonds go? Well, they behave and have certain properties based on what our structures look like. So next thing we're going to look at is what's called bond polarity and electronegativity. Now, I actually mentioned bond polarity in the last unit, I believe. If something is polar, a bond, if something has different electronegativities, so they can actually, like water is polar, so that is why it will attract to NaCl to dissolve it, because positive and negatives attract each other. So what is polar? What makes water polar? Well, it has to do with what's called electronegativity. Now, this is similar to electron affinity, things that like electrons. It's the tendency to attract a bonding pair of electrons. So like I said, you can think of it like electronegativity is like electron affinity. It wants electrons. They're a little bit different, but definition-wise, kind of similar. So the most electronegative atom is fluorine. Remember, these guys don't want any electrons, so we ignore the noble gases. Fluorine is the most electronegative, and then it kind of goes back from there. So electronegativity goes up and to the right, like most of our other properties do. Okay, increases from the left to the right, excluding the noble gases, and it decreases as we go down. As they get bigger, they aren't able to attract as much because of distance. Right, so the explanation is across the period. Remember, they get smaller. They have a higher electron affinity, so they also have a higher electronegativity. They are tending to attract those electrons. And down a group, they're very large, and they have a lower electron affinity. So then they kind of go together. You can see this chart here. Fluorine is my most electronegative, and then everything else kind of goes after that. And there's my graph. Now, these are the actual values for electronegativity. And there's a reason that I'm giving you these. I'm going to tell you here in a little bit. But again, these have no electronegativity. We call fluorine 4, and then everything else is kind of in relation to fluorine. So you'll see over here, my metals are very not electronegative. They don't really want electrons. Whereas fluorine really wants an electron. It's over here. Hydrogen is actually kind of somewhere in the middle. In the periodic table, hydrogen sits right here, but number-wise, it's very similar to carbon. Okay, so how do you get something to be what's called polar? Well, if bonded atoms have different electronegativity, so if you have things bonded together that have different attractions of electrons, it's going to be polar. Now, if you have two things bonded together that have the same electronegativity, so right, chlorine's electronegativity is 3.2. That means it like pulls on the electrons with a 3.2 strength. You can kind of think of it that way. Okay, so if they're bonded together, well, both chlorines are going to pull equally, right? They're both going to pull with a strength of 3.2. So they are actually going to share their electrons equally. This is called non-polar, because they do not have poles. Everything is the same. Now, if they don't pull equally is when you get poles. So a polar bond is something that's covalent. We're still talking about sharing. It's just that one kind of hogs the electrons. So if you have hydrogen bonded to chlorine, for instance, hydrogen has an electronegativity of 2.2, whereas chlorine has an electronegativity of 3.2. So it actually kind of like hogs the electrons, pulls them a little bit closer to itself. They're still sharing, but chlorine kind of hogs them a little bit. And this is when we get a partial charge. So it hasn't completely donated the electrons. So you don't get like +1 and -1. They have what are called partial charges because they're a little bit positive and a little bit negative, but they're not completely ionic yet. So this is a partial positive. It's a delta. That's the symbol. Plus means it's a little bit positive over here, and over here it's a little bit negative. And that's how we represent partial charges. And that's what you get when something is polar. It has like two poles, like a north and a south pole. It has a positive and a negative pole. Okay, so polar covalent bonds. This is only for covalent bonds. This is when the bonding electrons shared unequally between the two atoms because something kind of hogs them. So anytime you have differing or electronegativities, you're going to have something that is polar. And then when you get extreme differences in electronegativities, that's when you get an ionic bond. So it's really kind of a spectrum. Okay, so this one shares equally. This one, the chlorine kind of hogs it. But when you put sodium with chlorine, so sodium only wants an electron with a strength of 0.9. Sodium's like fine, you can have it. It completely donates the electron to chlorine. So that's when you get a complete transfer, and then you have an ionic bond. So instead of thinking it like two categories, like covalent is sharing and ionic is completely donating, it's really more of a spectrum. So things that share completely equally are covalent bonds, non-polar covalent bonds. As the electronegativity difference increases, so anything that has a difference of above 0.4 is going to be polar. So HCl that has a difference of 1, right, 2.2 to 3.2, that falls in the polar range. And then once they get really, really polar, one kind of completely takes the electrons, and that's when you get an ionic bond. So anything that has an electronegativity difference of above 1.7 is usually an ionic bond. So again, it's really more of a spectrum instead of just covalent is nonmetal, nonmetal, and ionic is metal, nonmetal. It just so happens that way that since metals are not very electronegative and nonmetals are, ionic bonds completely donate, and then covalent bonds are sharing. But again, there's a spectrum of nonpolar versus polar. Okay? So difference means polar. If there's no difference, then it's just a nonpolar covalent bond. Okay, so for example, before, I'd like you to try to describe the following bonds as either nonpolar covalent, polar covalent, or ionic. And yes, you can use these numbers to help you figure that out. Okay, so answer-wise, I have KCl. Now you should look at that and be like, that's a metal and a nonmetal, so it's an ionic bond. And yes, it is an ionic bond because one, it's a metal and a nonmetal, but also because it has such a difference in electronegativity. All right, K over here is 0.8, whereas Cl is 3.2. That is way more than a difference of 1.7, so it is definitely ionic. Now, NCl and CCl, we know they're both covalent. They're two non-metals bonded to each other, but are they polar or non-polar? Well, N and Cl, they do have different electronegativities, right? N has a 3 and chlorine has a 3.2, but that's only a difference of 0.2. So while chlorine may hog the electrons just a little bit, they're sharing pretty equally. So as remember, anything under a 0.4 roughly is going to be non-polar. So even though these are two different nonmetals, it is considered a non-polar bond. Whereas C and Cl, well, C has an electronegativity of 2.6, chlorine is 3.2, their difference is 0.6, so this would be considered a polar bond. So one side is hogging the electrons, so you got a partial charge of a little bit positive on one side and a little bit negative on the other side. Now, we can actually measure this difference in electronegativity. That's going to be called a dipole moment. It is a quantitative measure of polarity. So like, how polar is it? How different are they? Kind of similar to us comparing those electronegativities. So we call that a dipole moment. Means it has two poles, right? A little bit positive side and a little bit negative side. So that's why it's called a dipole moment. And the way that we represent those is with what's called a vector. Whether you've taken physics or whether you have watched Despicable Me, a vector is something that has both direction and magnitude. And the way we draw those is with an arrow. The bigger the arrow, that represents more magnitude. And whatever direction it's pointing is the way that the pole is going. So this is called a dipole. It is really just a vector. Okay. We always point it toward the more electronegative. So when we're drawing dipoles to represent a polar bond, you point it, the arrow goes toward the one that's more negative. Okay, so like toward fluorine, if you're talking about a polar bond. Okay, and then we write a little line over here, so it looks like a plus. That's the positive side. Okay, so this would be pointing toward the negative side. So anytime you draw a polar bond, and I ask you to draw the dipole moment, I want you to draw the vector. Okay. Now, when we start getting more complicated molecules, so things that aren't just like an N bonded to a Cl or a C bonded to a Cl, sometimes we have multiple things bonded to them, and that's how we get these like polar molecules. So molecules are actually more complicated, and we're going to get more into this in the next chapter. But what you do is you add the vectors to see if something is polar overall or not. So we know bonds are polar based on their electronegativity difference. We just talked about that, right? The electronegativity difference tells you if it's polar or not. But what makes a molecule polar? So if it's got multiple bonds. For example, water, this is actually the shape of water. It's not linear. It looks like this. It's called bent. That's again in the next section here. But since oxygen is much more electronegative than hydrogen, the vectors look like this. They point toward the oxygen. And when you add vectors together, if they cancel out or if they don't cancel out, that's actually going to tell you something's going to be polar or not. Again, I will get more into that later, but carbon dioxide is linear. So its vectors, this vector and this vector, are the exact same size because they're the same, carbon to oxygen. And they are in the exact opposite direction. So they cancel out. So carbon dioxide, the whole molecule, is actually non-polar because its dipoles that we draw cancel out. HCN, however, if I have hydrogen to carbon, well, carbon's more electronegative, just barely. So this should be a small vector. Whereas carbon to nitrogen, which is a little bit more polar, its vector looks like this. Notice I drew it bigger because it has a stronger pole. These actually don't cancel out because they're not in opposite directions and they're also not the same size. So they really just compound, and this would be called a polar molecule. But again, I'm going to get more into that in a little bit. Now, I did have a simulation linked up here I want to show you. Okay, so this kind of shows a dipole moment. So you'll see I have, here, I'm going to take everything off first. I have molecule A and molecule B. Let's start with them having both same electronegativity, middle. Say they're both like carbon or something. Okay, if I check the bond dipole box, notice there is no bond dipole because this molecule isn't polar if they have the same electronegativity. They have partial charges? No, because this is a non-polar bond. Okay, so now if I let's make this one less polar, electronegative, and this one more electronegative, so they have very large differences in electronegativity. My bond dipole looks like this. I have a partial positive on this side. This is the one that's less electronegative. And I have a partial negative on this side. This one is the one that's more electronegative. So these are kind of two ways to represent a polar bond. Is this dipole here, or writing partial positive and partial negative? You should be familiar with both. I like this electron density here because it kind of shows you that the electrons are kind of hogged over here. They stay more over here. Electrostatic potential is kind of the same thing where the negative and the positive are. And the other thing I want you to notice about these charges are that if you did put this in an electric field that has positive and negatives, it's actually going to align with, like, the positive will attract the negative of the field and the negative will attract the positive. So here, I'm going to put it like this really quick. I put it in an electric field, you'll notice it turns because this is the negative plate and positive will attract negative. And this is the positive plate and negative will attract positive. So it kind of like aligns in an electric field, kind of shows you that it has those properties. Now, if I had everything as the same electronegativity, I can move it however I want to, and it's not going to align in an electric field. Change this back, boom, it turns in the electric field. So it does have like these positive and negative attractions. Now, I was also mentioning what happens when you have multiple bonds. Well, here, I'm going to make all of these the same, less. This is, no matter what shape it is non-polar. Let's show that bond dipole. I got nothing because all of these atoms are the same. There's also no molecule dipoles. Now, let's go ahead and let's make it linear, but let's make B way more electronegative. Okay, so you'll notice now I have bond dipoles pointing in toward the middle. Now, these, since A and C are the same, these are the exact same size and in the exact opposite direction. So they will cancel out. I have no molecule dipole. I have no, partial charges because of the way that they go on. But there is no molecule dipole at all. Now, if I bend it, so the shape matters here. If I bend this molecule, it's not linear anymore. You'll notice that I do have a bond dipole because these are not in the exact opposite direction and they don't cancel out. So like this is CO2 and this is water. So the shape matters. Now, again, we'll talk about these more when we talk about 3D structures because, like I said, the shape actually matters. But I did want to show you this. So real molecule wise, that's a Java and we're not going to worry about that. And the last thing I want to talk about in this little section is, again, that from nonpolar to polar covalent to ionic bonds, it's really more of a spectrum. So we can say that things have a certain percent ionic character because it's not a black and white line, ionic and covalent. That's actually not how it works out. It's just that things are more ionic than others. If they completely transfer, the most ionic things that have completely different electronegativities, it's called an ionic bond. So if you're looking at the spectrum, things over here that are still ionic, but maybe they have a 1.8 or a 1.9 difference, don't have as much ionic character as things over here that have like a difference of 3 or something like that. So that's where percent ionic character comes in. Anything that has 50% or more ionic character is considered an ionic bond. 100% means there's a complete transfer of electrons. 0% ionic character means it is a non-polar covalent bond. There is no sharing. So if you look at this chart, again, it's like a spectrum. Electronegativity difference is down here, which is related to percent ionic character over here. The higher the electronegativity difference, like I was saying, things that have like a difference of 3 or 3.5, these things all have an almost 100% ionic character. Whereas down here, what was the one I was talking about earlier? CF or CH, I don't think that's on here. But IBR, for example, those are different, but let's see, what's their difference? Oh, they're not up there. Oops, sorry, scrolling too much. HCl, okay, HCl. That would be a polar bond. So it's polar, but it's close to 25% ionic. And then we're like anything above 50, we consider ionic bonds. So these are all ionic bonds. These are all covalent bonds. Anything over here is a polar covalent bond. So that's kind of another way of saying that they have a spectrum, and the higher the difference in electronegativity, the more ionic character they have.